Something is out there. Something enormous. Something so large that the moment scientists confirmed what they were looking at, the first instinct was to check the instruments, then check them again, then call in a second team, then a third, because what they were seeing did not fit, not in any model, not in any simulation, not in any theory of how planets form, how they grow, how big they're allowed to get before the universe itself intervenes and stops them. A planet, bigger than Jupiter. Not slightly bigger, not a little over the limit. Bigger in a way that forces an entirely new conversation about what a planet actually is, about where planets end and something stranger begins, about whether our solar system, with Jupiter as our giant, our protector, our king of planets, is actually as impressive as we always thought. Spoiler, it is not, because what scientists just found makes Jupiter look almost modest, and it raises a question that nobody fully expected to be asking so soon. How big can a planet actually get? The answer, as it turns out, is far larger than anything we were prepared for, and the story of how we found this world, what it is made of, what it is doing, and what it means for every planet we have ever cataloged, including our own, is one of the most extraordinary stories in the history of astronomy. It begins not with the planet itself, it begins with a shadow.
You cannot take a photograph of a distant planet the way you take a photograph of a mountain or a city. The distances involved make that essentially impossible with current technology. The stars nearest to us are 4 light years away. The planets orbiting them are tinier than specks next to the blazing furnace of their host stars. Trying to directly image them is like trying to see a firefly hovering next to a searchlight from across a city. So astronomers got clever. They developed a technique called the transit method. Here is how it works. When a planet passes in front of its star, from our line of sight, it blocks a tiny fraction of that star's light. The star dims ever so slightly for a predictable period of time. Then the planet moves on and the light returns to normal. By measuring exactly how much the star dims, and for exactly how long and with what regularity, astronomers can calculate the size of the planet, the length of its year, and the distance of its orbit. It is an elegant method, simple in principle, breathtaking in practice. The Kepler Space Telescope used this technique to discover thousands of exoplanets. NASA's TESS mission expanded the catalog further, and now James Webb adds spectroscopic power, the ability to analyze the light filtering through a planet's atmosphere and identify the molecules present. Together, these instruments have turned planet hunting from a rare, difficult art into something almost systematic. Almost. Because every so often, a planet comes along that breaks the system. A planet so large that when it transits its star, the dimming is not subtle. It is dramatic, unmistakable. A signal so strong that instruments designed to detect the faintest whisper of planetary transit register it like a shout. That is what happened here. The data came in and the dimming was extraordinary. The transit lasted longer than expected. The depth of the light curve, the shape of the dip in brightness, pointed to something with a radius that pushed against the upper limits of what any planetary formation model said was achievable. The team ran the numbers, then ran them again, and what they found sitting in the data, hiding in plain sight in the light curve of a distant star, was a world unlike anything in our catalog. A planet so massive it sits right at the boundary between giant planet and something altogether different, something the universe has a special name for. Jupiter is the largest planet in our solar system. It is not close. Jupiter contains more than twice the mass of all the other planets in the solar system combined. It is so large that more than 1,300 Earths could fit inside it with room to spare. Its storm system, the Great Red Spot, is a hurricane that has been raging for at least 350 years and is wider than the entire Earth. By any reasonable measure, Jupiter is a monster. But Jupiter is not alone in the galaxy. Astronomers have known for decades that gas giant planets can grow much larger than Jupiter. Hot Jupiters, giant planets orbiting extremely close to their host stars, were among the first exoplanets ever discovered. Bloated by the intense radiation of nearby stars, their atmospheres puff outward, making them larger in volume than their mass alone would suggest. But this new world is something different. It is not just inflated, it is genuinely, fundamentally massive. Its radius stretches to roughly 2 times that of Jupiter. Its mass pushes toward the upper boundary that separates planet from a class of objects called brown dwarfs. Brown dwarfs are sometimes called failed stars. They form the same way stars do, from collapsing clouds of gas, but they never accumulate quite enough mass to ignite sustained hydrogen fusion in their cores. They glow with residual heat for billions of years, slowly cooling, dimming, fading. The upper mass limit for a planet is generally placed at around 13 Jupiter masses. Above that, an object starts to fuse deuterium, a heavy form of hydrogen, and enters brown dwarf territory. This newly discovered world sits tantalizingly close to that line, close enough that the debate has already begun. Is it a planet? Is it a brown dwarf? Or is it something in between, a class of object our categories are not quite equipped to handle? And it gets stranger. Because of where this world is located, it orbits its host star at a distance that should make its formation almost physically impossible according to standard planetary formation theory. The leading model, called core accretion, says that giant planets form in the outer regions of solar systems, where ices can condense and help build the massive solid cores that then rapidly accumulate gas. At the distance this planet sits, scorched by the heat of its nearby star, core accretion simply should not work. The building materials are wrong, the temperature is too high, the conditions that allow gas giants to form are absent. And yet, there it is, enormous, defiant, sitting exactly where it should not be. Scientists have a candid explanation. They think this world may have formed far out in its solar system, in the cold, icy regions where giant planets belong, and then migrated inward over millions of years as gravitational interactions with the surrounding disk of gas and dust slowly drained its orbital energy. It is a journey of billions of kilometers, a slow spiral inward toward its star over millions of years. And when it arrived in its current orbit, the star's radiation began to work on it, heating the upper atmosphere, causing it to expand, making it bigger, not more massive, but physically larger in volume as the gas puffs outward. The result is a world of extraordinary, almost theatrical scale, a planet that wears its size like an announcement. And inside that enormous atmosphere lies chemistry so alien, so far removed from anything in our solar system, that the scientists studying it have compared it to reading a document written in a language that shares the same alphabet as English, but follows completely different rules. One of the extraordinary things about the James Webb Space Telescope is what it can do while a giant planet transits its star. As the planet crosses in front of the stellar disk, some of the star's light passes through the planet's atmosphere before reaching our instruments. Different molecules in the atmosphere absorb different wavelengths of light. By analyzing precisely which wavelengths are missing from the starlight we receive, Webb can construct a chemical portrait of the planet's atmosphere, a recipe written in light. And the recipe for this enormous world is extraordinary. Water vapor, detected. One of the most fundamental molecules in the universe, present even in the swollen atmosphere of a gas giant far larger than anything in our solar system. Carbon dioxide, present. another key molecule, a molecule that on Earth is breathed out by every living organism, that regulates the temperature of our atmosphere, that James Webb has now found in the air of a planet orbiting another star. Methane, detected. A molecule with a particular significance because on Earth and in our solar system it is associated with both geological and biological processes. And something else, something the team did not expect to find in a planet this large, this hot, this far from conditions we would normally associate with complex chemistry: sulfur dioxide. Sulfur dioxide in the atmosphere of a giant exoplanet is not just a chemical curiosity, it is a thermometer, a clock, a window into the energy dynamics of the planet's interior. On Earth, sulfur dioxide is produced by volcanic activity and industrial processes. In a planetary atmosphere, its presence tells scientists about the internal heat, the chemical cycling, the geological activity of the world beneath the clouds. This planet is not dead. It is not a passive, inert ball of gas drifting around its star. It is active, dynamic, churning, a world in the process of becoming, of evolving its chemistry, cycling its elements, behaving like a system rather than a sculpture. And here's the thought that nobody says out loud, but everyone has. If chemistry this complex is happening in the atmosphere of a giant gas giant far larger than any planet in our solar system, what is happening on the surfaces and in the oceans of the smaller rocky worlds orbiting in the habitable zones of their stars nearby? This world is not a candidate for life, too hot, too massive, too turbulent. But it is a proof of concept, a demonstration that the universe builds chemistry at every scale, that molecules do not just appear on comfortable Earth-like worlds, that carbon and water and sulfur and the raw materials of biology are present across the cosmos in environments we would never have thought to look. If chemistry exists here, in the bloated, scorching atmosphere of a superjupiter on the edge of becoming a failed star, then the universe is far more chemically generous than we imagined. And the implications of that generosity stretch far beyond this one enormous world. They stretch all the way back to the question of whether we are alone. We are drawn to the biggest things. It is a deeply human instinct. The tallest mountain, the deepest ocean, the largest creature, the longest river. We measure the world in superlatives because superlatives feel like understanding. They feel like we have found the edges of something, the limits. And then the limits move. A planet bigger than Jupiter should have been impossible to miss, and yet, for most of human history, for the entire span of civilization, from the first cities to the first rockets to the first space telescopes, we had no idea it existed. It was always there, orbiting its star, puffed up and enormous, and completely indifferent to our ignorance of it, until we built something powerful enough to see it. And this is the pattern that repeats itself over and over in the history of astronomy. Every time we build a better instrument, the universe reveals something that does not fit our current understanding. Every time we look deeper, something comes back that forces us to revise our models, expand our categories, reconsider what we thought were settled questions. Galileo turned a telescope on Jupiter and saw 4 moons orbiting it, proof that not everything in the universe orbited the Earth. The universe got bigger overnight. Hubble photographed distant smudges in the sky and showed they were entire galaxies, billions of them. The universe got incomprehensibly larger. James Webb found a planet bigger than Jupiter sitting in an orbit where our models said no giant planet should be, wrapped in an atmosphere more chemically complex than any exoplanet atmosphere we had measured before. The universe expanded again. It always does. And here's what that pattern teaches us, if we are willing to learn it. Our models are not the universe. Our models are our best current attempt to describe the universe. They are extraordinary achievement of human reasoning. They are built on centuries of careful observation and brilliant mathematics and painstaking experiment. But the universe is not obligated to respect them. It does not check our papers before creating a planet. It does not consult our simulations before placing a super-Jupiter in an orbit where we said it should not exist. It simply does what the laws of physics allow. And the laws of physics, it turns out, allow considerably more than we keep assuming. Every impossible discovery is a correction, a gentle or sometimes not so gentle reminder that the map is not the territory, that our understanding of nature is always a work in progress, that certainty in science is not a destination but a direction. And what a direction it is! We live on a small, warm, beautifully ordinary planet orbiting an unremarkable star in one arm of an average spiral galaxy. By cosmic standards, we're nothing special, nothing unusual. But we built telescopes. We pointed them at the sky and refused to accept that what we could not see did not exist. We developed instruments sensitive enough to detect the shadow of a planet crossing a star 1,000 light-years away. We built a space telescope folded like origami, launched on Christmas morning, that can read the chemistry of alien atmospheres by analyzing the wavelengths missing from starlight. And with those tools, we found a world bigger than our biggest world, a planet that should not exist where it is, that defies the model, that carries impossible chemistry in its inflated atmosphere, and orbits its star as if the rules never applied to it. That planet does not know we found it. It does not know we named it. It does not know that scientists on a tiny blue rock 1,000 light-years away stayed up through the night checking data and running calculations and quietly revising everything they thought they knew. But we know. And knowing, truly knowing something about a world that has never been touched by human hands, never warmed by human presence, never observed by any eye before ours, is one of the most profound things our species has ever learned to do. There's a planet bigger than Jupiter out there. We found it. And somewhere in the data we collected, in the light curves and the spectral lines and the chemical signatures, the universe is leaving us a message. Keep looking. There is always more.